Hi. Today we are going to talk about one of the most important concepts in linear algebra. That is the notion of a linear map or linear transformation between two vector spaces. And it's a very interesting thing. See, suppose I have two sets x and y, then what kind of maps I can look for f from x to y? Nothing specific, unless I want f to be 1, 1 or on 2 or a bijection. Nothing else I can require, demand. But if x and y have additional structure, let us call it v and w vector spaces, okay, then what do I look for is I look for maps f from v to w which respects the structure. What do I mean by which respects the structure? See, when v, it's not a set, it has additional structure. Namely, I can add two vectors, I can scalar multiply to a vector. Okay, this kind of thing should be protected or respected or preserved. That means if I take vectors v1 and v2 in the domain, I can add them v1 plus v2, right? Then let's look at f of v1 will be a vector in w, f of v2 will be a vector in w. Then I can add them there. I will get f of v1 plus f of v2 in w. Here I will have v1 plus v2 in v. Now I can look for f of v1 plus v2. That will be a vector in w. What do I need? I want f of v1 plus v2 equals f of v1 plus f of v2. That is what I mean by saying f respects vector addition. Okay, and you may think it's abstract. It's not abstract, because let us look at, suppose I have something like one $5 bill, one $10 bill, right? And today's exchange rate is, let us make life easy, 80 rupees per dollar. Then if I give $5 bill, then I should get 400 rupees. If I give a $10 bill, I would get 800 rupees. So I will get in all 1200. Or I could have added this $15 I give it to the money exchange guy. He would have given 15 times 80, that is 1200. You understand that? My F is, for each dollar I get 80. Therefore for $5 I will get 400. For $10 I will get 800. Therefore if I exchange both the bills, what do I get? I get 1200. Instead, I add here, I say, okay, I have $15, you give me. How much you will give me? 1200. See, this is what we want. Okay. So without much further ado, let's share the screen, start doing the work. So, and it's also very important, suppose you want to understand a human being, then how do you understand him better as a human being? The way he deals with variety of people. A person who is a beggar, a person who is rich, a person who is a subordinate, a person who is his superior, a person who is his student, a person who is his teacher, okay, a person who is a child, or he is father of somebody else, father of somebody, or he is looks at, he is a child of somebody, his father. So the way he deals with these kind of people give us some kind of an idea what the human being is. Similarly, when I want to understand a vector space or any mathematical object with an additional structure, what we look for is we look for maps which preserve this. Okay. Okay. If it's a bit abstract, don't worry. Keep it in mind. You will gradually understand the meaning. Okay. So what do I have now? I have two vector spaces v and w. Okay, I am looking for a map f from v to w. Notice that usually algebraists prefer the notation f between t and w. Analysts usually will write t from v to w. So I may interchange f and t, whichever suits me. Okay, it appeals to me at that moment. So do not get confused. Okay, so what do I have now? I have v So let me write as this. Okay, this is my V. Okay, this is my V1. Let me call it X and Y. Then this is my X plus Y. This is my V. Then this is my F. Okay, this is my W. Okay, then what happens? This is my Fx. This is my Fy. And this is my F of Fx plus Fy. Okay, now what do I want? This goes to this, and this goes to this, and this goes to this. Where should it go? F of x plus y should be, okay, x plus y, where will it go? X plus y will go to this. But what do I want? I want it to be the addition of the vectors in W, fx plus fy. You understand this? Okay. And similarly, scalar multiple. So I have a vector x and I have a scalar t, then t dot x will make sense. And that's a vector in V, therefore this is a vector in W. And let us look at fx is a vector in W and t is a scalar, therefore t dot fx makes sense. So what do I want? I want this to be equal. Okay, so let us write the definition. A map F from V to W is a linear map. I usually say linear map because it's easier, but most often beginning textbooks will say linear transformation because it's a map which has some additional property. We call it linear map. Any function from x to y is called a map. Therefore, any function or any map from F to V to W will be a map. It should have some additional property, then I will call it linear map. If the following are true, what is it? For all x, y in V, okay, I can add x plus y in V and look at its image f of x plus y in W. This should be, take the image of f, x under f, image of y under f, and add them in W. These are vectors in W, this equality should hold. What are this? This is an addition in V. This is addition in W. Okay, all right. So this should happen. And second condition is for t in R and x in V, let us look at f dot t dot x. See, this is a vector in V and therefore f of that will be a vector in W. Let us look at fx, that's a vector in W and therefore I can scalar multiply by this t. Then these should be the same. Right? Again, go back to my dollar exchange problem. Now I have to, okay, 5 $10 bills. So for each $10 bill, I will get 800 rupees. Therefore, if I have 5, then I can have 50 into 800, or I can say for each $10 bill, I got 800. For 5 $10 bills, I will get 5 times 800. That is 4,000. Here, 5 times 10 will be 50. Therefore, f of 50. Are you following? F of 5 times 10. This should be equal to 5 times f of 10. F of 10 is 800. Therefore, 5 times that will be 4,000. This will be 50 into 800. F of this will be 50 into 800. So they are equal. Okay. So please take some time. Understand this. Okay. This is a very easy notion. Do not get psyched or intimidated. Now let's look at an example. Okay. I'll give some, to give you an idea, I'll start with a very simple minded example. Okay. But some examples are very close to my heart. I will come to that immediately after this. But let us look at, suppose my V equal to R2 and is also equal to W. Right. Now let's look at the map you have from V to W. So for any vector f of x, y, okay, I am writing it, let's say x plus y and 3x minus 2y. Okay, I want to know that this is a linear map. So what are the things I should check? I have x1, y1, this is a vector, x2, y2, this is a vector, and add them. What will I get? I will get x1 plus x2, y1 plus y2. Okay. Now I should look at the image of f x1. That will be x1 plus y1, 3x1 minus 2y1 plus the image of x2, y2. That will be x2 plus y2, 3x2 minus 2y2. You understand? Now I add these two things. What do I get? This is f of x1, y1. This is f of x2, y2. Now I have to add. When I add, what will I get? So I can do x1, y1, x1 plus y1 plus x2 plus y2. I rewrite it as x1 plus x2, y1 plus y2. And similarly, I will do that 3 times x1 plus x2 minus 2 times y1 plus y2. Do you accept it? That is what this is. But where this, what will be f of x1, x2, y1 plus y2? This according to us, the first coordinate, the the first and second coordinates must be added. Therefore, it will be x1 plus x2 plus y1 plus y2. That is the first coordinate here. Next one will be take the 3 times the first coordinate, that is 3 of x1 plus x2 minus 2 times the second coordinate, that is 2 of y1 plus y2. So are they equal? Yeah, because this is f of x1 y1 plus f of x2 y2, and this is f of x1 plus x2, f of y1 plus y2. They are equal. Therefore, f respects vector addition or preserves. Yeah. Now what is the next one I have to check? I have to check scalar multiplication. Take t in R, then t dot xy will be tx ty. So under f, where does it go to? Go back. It says add the x and y coordinate, that is t times tx plus ty, and next one will be 3 times the first coordinate, that is 3 times tx minus 2 times ty. Do you understand? Right. Okay. Now what is f of xy? That is x plus y, 3x minus 2y. Therefore, t times f of xy will be 3 times xy, that is 3x plus, sorry, t times x plus t times y, and then and then t times this is t times 3, that is t 3x minus 2y. Are they equal? Yes, they are equal. Therefore, we have shown f is a linear map. From R2 to R2. Okay, go through this example. So as an exercise, do something more generally. Let A, B, C, D be real numbers. Okay, define f from R2 to R2 so that f of xy equal to ax plus by and cx plus dy. Okay, this is the definition. Check f is a linear map. Notice that in the earlier case, a equal to b equal to 1 and c equal to 3, d equal to minus 2. Okay, so the last earlier example is a special case. Okay, is a special case of this exercise. Okay, so pause, review, proceed. Just to do this once, you will become more comfortable before you go further. Okay, all right. I want to look at first some of the simple examples. Okay, these are the things which usually people don't do. And in an interview or exam, when you ask, students do not know. Now we know R is a vector space over itself. Therefore, I can look at the domain and range, both are the R as a vector space over itself. Then I can ask, suppose F is a linear map from R to R. Okay, notice that I have not given what the map is. Suppose it's a linear map. Okay, okay. I want to understand. Okay, okay. Understand. Yeah, that is determine F. I want explicitly determine F. Okay, it's not as difficult as it is. It also teaches one important fact we have to learn about linear maps. Okay, now suppose I start one as a vector in R. Okay, I consider this as a vector. Then one, this is a basis for R. What does it mean? Give me any real number x in R. This I can consider as a vector, but this vector x is x times 1, where I think of 1 as a vector, this as a scalar. You understand? It's just your viewpoint. That's it. Okay. Do not get psyched. It's the same thing. It is product of two numbers. Okay. But I can write this, right? Now, since f is a linear, what do I know? F of x must be f of x dot 1. Now, I'm going to pretend x is a scalar and y is a vector. Since f is a linear map, what do I know then? It should come as x times f of 1. X comes out, then f of 1. Do you understand this? Okay. I just use only the f respects scalar multiplication. That's it. You understand that? Okay. Now suppose does it, so let us let lambda equal to f of 1. Therefore f of x is equal to lambda times x, where lambda is f of 1. Now is you know, so using only f respects scalar multiplication, I found fx is of the form lambda x, but I do not know yet whether it is whether it respects addition. That also I have to check. But that's very easy. Suppose x and y are real numbers, that is, consider them as vectors. Then what is f of x plus y? According to us, it should be f of x plus f of y, right? But what is f of x? That we already saw. It is lambda x plus lambda y. But what is this? This is lambda times x plus y. Now what is f of x plus y? For any real number z, f of z is lambda times z. Now z is x plus y. Therefore, it's lambda times x plus y. So any such map is automatically additive also. Please pay attention. So what I have proved, I do not know, you just gave me f is a linear map. Then I found out f is of the form lambda x, where lambda also I know what is it is f of 1. This is for all x in R. And any such map is linear. Okay. So f is linear, then define lambda equal to f of 1, then f of x is lambda times x. This is correct. And this f is at linear map. Okay. Conversely, fix a scalar alpha and define f alpha of x equal to alpha times x, then f alpha is linear. Why? It's very easy to check. What is f alpha of x? It is alpha dot x. Therefore, f alpha of x plus y will be alpha times x plus y. Distributive law will give me alpha dot x plus alpha dot y, which is f alpha of x plus f alpha of y. Therefore, it is f alpha respects addition. And f alpha, does it respect scalar multiplication? That is same as alpha times tx. Notice that alpha, tx are all real numbers. Therefore, associativity and commutativity will tell me this is same as t times alpha x. This is t times f of x. Therefore, f alpha respects scalar multiplication, right? Therefore, f alpha is linear. Now, what is f alpha at 1? That is 1 alpha. Therefore, therefore, we have classified all linear maps. R to R. What do I mean by that? We say that any linear map f from R to R is of the form f of alpha. Okay, any f is of the form f of alpha where f of alpha, where alpha is f at 1. Okay, take some time. This is will slightly abstract. Usually in the first course in linear algebra, people don't want to do that, not at the beginning. But I am doing it because I know you are good. You can understand. Okay. Now I want to extend the same trick which I used in R to R. So let V equal to Rn, W equal to R. I want to know, okay, classify linear maps F from Rn to R. Do not lose heart, pay attention, you will enjoy this. So this is a linear map, right? Now start with the vector x in Rn. Do you remember we have a basis B of Rn, E1 to En? This is the standard basis. EI is, if you write in row notation, row vector notation, 0, 0, 1, 0, everywhere 0 except ith place. Here also 0, here also 0. Okay, then we can write x as summation xi ei, that is x1 times 1, 0, 0, 0 plus x2 times 0, 1, 0, 0 and x1 times 0, 0, 0, 1. You understand? Right. Now suppose f is a linear map, right? If f is a linear map, then what should be f of x? F of x will be f of x1 e1 plus x2 e2 plus dot 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 xn en. Now f is, f respects addition. There is addition of this vector and these vectors. Therefore it will be f of x1 e1 plus f of x2 e2 plus dot 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 plus f of xn en. Do you understand this? This is because why? This is f respects addition. Okay, because of that. Now f also respects scalar multiplication. Therefore, what will be f of x1 e1? That will be x1, because remember x1 is a scalar, e1 is a vector. Therefore, it's x1 times f of e1 and x2 times f of e2 plus xn times f of en. Solid. You understand this? Right. Now, what is something interesting? Now, notice that this is a number, this is a number, x2 is a number, f of u2 is a number, xn is a number, f of en is a number. Therefore, let me call alpha I equal to f of ei. This is a real number. Therefore, I can write f of x equal to alpha 1 x1 plus alpha 2 x2 plus alpha n xn. Where, what is alpha I? Do I know alpha I? Yes, that is f of ei. You understood that? So now let's go back. This is exactly similar to R to R case, right? F of x equal to f of x dot 1, x comes out, f of 1, that 1 I called as lambda, then f of x equal to lambda x. So same thing happens here. Are you following? Yeah. Now notice that we used both the fact that f is additive as well as f is f respects scalar multiplication. Okay. Okay, both the facts we used to arrive at it. Okay, so let us call given a vector alpha as alpha 1 to alpha n, this vector where in Rn. Okay, now I claim, let us define f alpha of x. This is a definition equal to alpha 1 x1 plus alpha n xn. Then this is a real number. I claim f alpha is linear map. Okay, it's very easy to check. Okay, what is f alpha x plus y will be? So x plus y will be x1 plus y1, etc. xn plus yn. Therefore, f alpha that will be alpha 1 into x1 plus y1 plus alpha n into x1 plus yn. Is it okay? But what is f alpha x? This f alpha y, alpha 1 y1, alpha n yn. Therefore, what is f alpha of x plus f alpha of y? That is alpha 1 x1 plus alpha n xn plus alpha 1 y1 plus alpha n yn. But now I can group terms collecting alpha 1. Therefore, it's going to be alpha 1 into x1 plus y1 and plus alpha n into xn plus yn. You can see this side and these are equal. Okay, and hence we conclude these are equal. Right? You understand that? Okay. So what do you think I have shown? And now similarly you have to claim f alpha of tx equal to ti times f alpha x. Go back, f alpha tx will be tx1 txn. Therefore alpha 1 tx1 alpha n txn, but t is common, I can take it out. T times alpha 1 x1 plus dot 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 plus alpha n xn. That is t times f alpha x. Okay, check that. So what you have shown that? Now we have shown that if f is any linear map from Rn to R, then f is of the form f of alpha of x for all x in Rn, and I know what is alpha. The alpha is a vector which is f at e1 comma f at en. Okay, so take some time, understand. Okay, these are all non-trivial, so pause, review, proceed, spend at least a couple of minutes before you proceed. Okay, now let's do one more example. Let v equal to r m. I consider this as column vectors. That is, any vector here I will write not as this, I will write it as x1, x2, xn. Therefore, my ei will be 0, 0, 1 at ith place, 0 here. Ith coordinate is 1, all other coordinates are 0. Therefore, my x will be again the same thing, x1 u1 plus xn en, except I want it x em. 1 less than or equal to I less than or equal to m. Okay, right. Instead of writing row, I am writing column. You will understand why I am doing that. Now, let A be an m cross n matrix. So n cross m matrix. N times m, where n is a natural number with real entries, right? Then I want to define, let's take a vector x in V. Notice that this is a vector, column vector, therefore I can think of it as a matrix, m times 1 type matrix, because m rows are there, only one column. You understand? Therefore, the matrix multiplication A dot x is, this is the matrix multiplication. This makes sense because this is n times m and this is m times 1. Therefore, what will I get? That will yield me n times 1 type matrix. That is again a column vector. Okay. Therefore, where does it live? When I want to think of this as a column vector, where does it live? X lived in Rm, and this is n cross 1 matrix. That is same as saying a column vector with n entries. Therefore, I can think of this as a vector in Rn. Do you understand this? So now I define a map F given A, fix. A is fixed. Okay, fix. Then define a map if you want, define FA, but I will write it F because it will be more too much to write this. FA from Rm to Rn. Okay. F at X is A dot X. Okay. This is also column, this is also column vector. Okay. If I forget, don't get perturbed. In this particular context, we are thinking only column vectors. Okay. You should not get them in what up. Oh, sir, forgot to write C. Okay. Right. Is this clear to you? Yeah, because this is n cross 1, therefore I can think of as a column vector. Okay. So I got a map. What therefore I have a map from this vector space to this vector space. What is the question I want to ask? Is F linear? Okay. Now I am going to depend upon your earlier knowledge about matrix algebra. Okay. So that I don't have to spend time on that. Okay. So if you give me two vectors x and y in RMC, then x plus y, what is that? I have to check whether this is equal to fx plus fy, right? But what is fx plus y? That is a dot x plus y. But remember, x is a matrix of type m cross 1, y is also a matrix of type m cross 1, and matrix multiplication is distributive. Therefore, this is same as a dot x plus a dot y. But this is same as fx plus fy. You understand this? Yeah. A of, I'm sure you would have done this. This is equal to AB plus AC. That is matrix multiplication is distributive whenever these things make sense, of course. Because this is of n cross m. This I want to be m cross some k. I don't care what k. Then I will get AB will be n cross k, and this also n cross k. Therefore, addition is also makes sense. Okay, this you must have seen. This is a fact. You must have seen it earlier in matrix algebra. You understand? Therefore, F respects, okay, addition. Addition where? In R and C. Okay. But you will simply say addition. Now, scalar multiplication is again the same thing. F of Tx will be A times T dot X. But remember, this is same as T dot A dot X, which is T times Fx. Because T is a scalar. This also you know from matrix algebra, right? Therefore, what have we shown now? Give me any matrix, n cross m matrix, it gives rise to a linear map Fa from the column space to the column space. Okay, this is a linear map. Notice that the very first example and its generalization, the second example, okay, these are actually special cases of this. 1 and 2 are special cases of this. See, note 1 and 2 are special cases. Notice that 1 is already a special case of 2, therefore it's enough if we show 2 is a special case of this. Example 4 or 5? 4. Okay, why? Notice that if I look at the matrix A, B, C, D and write xy as a column vector, okay, this is going to be ax plus by and cx plus dy. This is 2 cross 2, this is 2 cross 1, this is 2 cross 1. Okay, here I am writing a column notation, whereas there I wrote as a vector notation. Otherwise there is no change. You see that? Ax plus by, cx plus dy. Right? Just to make sure that you all of a sudden why I changed to I started considering vectors in RNS column vectors. Why not as a row vectors? There is no problem. I can still do that, except it will be different kind of map. What do I mean by that? Suppose I take A to be an n cross m matrix, right? Then take a vector x. Now, if you want, this is example 5, but this is in place of column, I'm thinking of row. So I think of x1, x2, xn in Rn. Therefore, this I can think of as 1 cross n matrix, right? Therefore, if you give me a matrix A, which is A n cross m, so what kind of multiplication makes sense? Only this multiplication makes sense. This is a matrix product. This makes sense because this is 1 cross n, this is n cross m. Therefore, the result will be 1 cross m. Therefore, where does it live? It is 1 cross m. That's a row vector in Rm. Therefore, what will I get? I will get a map f. Okay, call it GA. This is a map from Rn to Rm now. And GA of the row vector x into xn is by definition x dot A. That is x1, x2, xn times A. Do you follow that? Again, you can check this is a linear map. Okay, right. So we have seen these things, but you can also do these things come naturally? Yes, I'll quickly go through some of the standard thing. Okay, some of the facts which requires various things, facts from analysis. Okay, suppose xn is a convergent sequence. Okay, then let's look at C, all convergent sequences in R. We have seen this is a vector space, right? Now okay, I will write x equal to xn. Okay, I will write this. So fx, I write it as limit xn because it's a convergent sequence. Therefore, the limit exists. Call it xn. You understand that? Okay. Now I claim f is from a map to R. This is linear. This you have seen in analysis, you must have seen or you will see soon, because if xn is convergent, yn is convergent, xn plus yn, this is a sequence. What is this definition? This is xn plus yn. And what is the limit xn plus yn? This is limit xn plus limit yn. But that is f of x plus f of y. This is f of x plus y. So, and similarly scalar multiplication, right? Because t times xn, and therefore limit of t times xn is t times the limit of xn, right? If xn converges to x, then c times xn converges to cx. You know this, right? I'm using that here. Therefore, this is a linear map. You see that these things come naturally. And another thing you might have seen is, Suppose I look at all differentiable functions on 0, 1. This is okay. This is a notation. This is C1. This is f from 0, 1 to r. If you do not know these things, okay, let me stick to easier one. Let us look at okay V to be the vector space of all polynomials. Let us say of degree less than or equal to n, and n is a natural number greater than or equal to 1. And W to be all polynomials of degree less than or equal to n minus 1. Then I have obvious map V from V to W. Now can anybody guess? I said I'm starting with the polynomial of degree n. I'm going to end up with a polynomial of degree n minus 1, not necessarily n minus 1. You see that intuitively, and you should see that the degree drops down, and I'm denoting the map by D. Can you guess what map I'm thinking? I'm sure if you think you know, I give a polynomial of degree n, and I may get it. The image will be polynomial of degree n minus 1 maximum. It may even drop down with maximum, it may be n minus. And I'm denoting calling the linear map, denoting it by capital D. D of, suppose F is P is a polynomial, D of P is P dash, the derivative. Yeah. Now you know that that is D of P is P dash. Therefore, D of P plus Q is, if P and Q are here, then D of P plus Q will be P plus Q and its derivative. But you know from calculus it is P dash plus Q dash. And similarly, D of, okay, notice that this is a constant. So let me write instead of T, now I will write it as a constant C. C times P, this is Cp dash, but C is a constant, therefore C times P dash, right? Therefore, this is a linear map. You see that? Linear maps arise very, very naturally. A third thing, again in analysis, okay, is the following. What is that? I hope you know something about integrability, etc. But let's not worry about. But I pretend as though that you know something, right? Some functions on, okay, for which I can talk about integral. Okay, so V is set of functions, say on the interval 0, 1, so that integral fx dx makes sense. Okay, if you know something about integration, it's okay. Assume it's continuous, and you pretend for a continuous function interval 0 to 1 fx dx makes sense. Just assume that. Okay, this is just to say how things occur. So if you are slightly uneasy, do not trouble yourself too much. Later you will understand. Right now, from V to R, I have a natural map. Then we take f and map it to 0 to 1 f of x dx. I claim this is a linear map. Okay. Now you see that the f is here as a function. Therefore, I don't want to call this as f. Now I would like to call it as t. You understand that? Now what I have to check? T of f plus g. But this, you know, integral of 0 to 1 f plus g at x dx. This is integral 0 to 1 fx dx. But that is integral 0 to 1 fx dx plus integral 0 to 1 gx dx. That is t of plus tg, and so on. Okay, therefore this is also a linear map. One has to check scalar multiplication, but that's easy. So, okay. Anyway, essentially I'm assuming that you know these facts, and in analysis we will give you a proof for this also. Okay. Now the next, before I close the lecture, okay, I want to know, is there any simple recipe which will tell me if you give a map f from Rm to Rn, when it is linear? You understand the question? This is any map. A map is given. I do not know whether it's linear or not. Now I want to know, can I find out linear map? It requires little thinking. It's not difficult. Okay, just bear with me for a while. First, to attend to this, let me observe if F is a linear map from V to W, then F of 0, this 0 is the 0 vector in V. Usually teachers will write like this, but I always assume my students are more intelligent than I am. Therefore, when I write f of 0, what is the domain of f? It is B. Therefore, this 0 must be 0 vector in V. You don't know to write. And I say it's equal to W is 0. Now, what is this 0? This 0 vector in W. Why? F, f of any vector in V is a vector in W. So, you are writing 0. Therefore, this must be 0. Does this make sense now? I am going to write only this hereafter. Yeah? This I claim. I have to prove this. But that's very easy. Why? Because 0 is in B if you want, right? Notice that 0, this is 0 vector and this is 0 scalar. This is 0 vector. You understand? If you want, I will write it for your sake. Is that clear? This is a real number. Yeah? Therefore, f of 0, 0, this 0 is a scalar, this is a vector. This is equal to 0 scalar and f of 0, this is a vector in W. Right? Okay. This is because f is linear. But this is any vector, 0 times any vector in a vector space we know is a 0 vector. Yeah? Therefore, but this is same as f of 0. Because 0 times 0 is same as 0 vector. Therefore, f of the 0 vector is the 0 vector of W. Okay? Please go through, pause, review, and then proceed. Okay? Now I'm going to use this fact to classify, to understand how do I recognize whether this is a linear map or not. Okay? The first thing is, I will not be able to complete it because I don't know. Okay? If f is Rm, notice that if x is in Rm, now at present we will assume this is a row vector so that it will be easier for me, f of x. This will be a vector y1, y2, yn in Rn, right? But this vector, this y1 depends on x. You understand? Let us go back to our R2, the first example. F of xy was x plus y and 3x minus 2y. You understand? This is your first coordinate in the domain, codomain. Therefore, this is your y1. Therefore, what is it? It's a function of this here. You understand that? Therefore, I can write this as f1 of xy is x plus y. Are you following? Okay. This y1 I will call it as f1 of x, and this y1 I will call it fn of x. And what is f2 of x here, xy here? It is 3x minus 2y. Yeah? Are you with me? Okay. Just nothing to the linearity. Let me say f of xy equal to e power x cos y, e power x sin y, and x times y. Okay, the f is a function from R2 to R3. Right? Therefore, this is your first coordinate in R3. This is the second coordinate in R3, third coordinate. But each of the coordinates is a function of x and y. You understand? Therefore, I can write this as f1 of xy. What is f1 of xy? It is e power x cos y. What is this? This is f2 of xy. What is f2 of xy? It is e power x sin y. And this I can write as f3 of xy. What is f3 of xy? X times y. You understand? So any from Rm to Rn, I can write as f of x equal to f1 of x and fn of x. Therefore, f1 for each I, this is going to be a function from Rm to R. Do you understand this? This is a function from Rm to R. Okay? Are you with me? Don't lose heart. Okay? Now I am going to claim f from Rm to Rn is linear if and only if each fi from Rm to Rn R is linear. This is what you want to prove. Is it clear? Yeah? Okay. So we want to prove this. One way, let's assume f is linear. Okay. Then let us look at x plus y or x plus z. X and z are in Rm. Okay. Then what will it be? F of x plus z. I know it is f of x plus f of z because of linearity. This is linear. F is linear, right? But f of x plus z. Okay. This is what? This is f1 of x plus z and f1 of x plus z. Do you understand? Because what is f of x? F of x is f1 of x, f1 of x. You understand? Therefore, I am writing the coordinates, and the coordinates will be function of x plus z. And here, what do I have? This I will have f1 of x, f1 of x plus f1 of z and f1 of z. Okay, these are two vectors in Rn. But what is the sum of these two vectors? That is f1 of z, f1 of x plus f1 of z plus f2 of x plus f2 of z dot dot. The last one will be f1 of x plus f1 of z. Do you understand? This is a vector in Rn. This equal to this, and addition of two vectors I am writing. But since f is linear, what do I know? These two vectors must be the same. That means the first coordinate of the left hand side must be the first coordinate of the right hand side. That means f1 of x plus z must be equal to f1 of x plus f1 of z. For which x and z? For each x and z. So what does it mean? F1 respects addition. Similarly, each fi respects addition. Right? Okay? And similarly, scalar multiplication. Why? F of t times x. Okay? This is t times fx because f is linear. Right? But what is this? This is f1 of tx dot dot fn of tx. That's a component form of the f. But what is this? This is t times f1 of x, f1 of x. Because f of x is this t times. But how the scalar multiplication is defined? That is t times f1 of x, comma t times f1 of x. Now since f is linear, these two are equal. That means these are equal. That means f1 of tx must be equal to t times f1 of x and so on. Therefore, for each I, this must be true. And for which x for all vectors x in Rm. For which t for all scalars. Therefore, it says each fi respects scalar multiplication. So what I have proved? I have proved F linear implies each Fi linear. Yeah? Do you accept it? Very good. Now what is the advantage? The advantage is I know what is Fi. Fi is a linear map from R M to R. Notice that in our example earlier, I don't remember, I think example number 4 possibly. Yeah, example number 3, we had already identified what are all the linear maps from Rm to R. They are given by F alpha. What is F alpha? That is f of x equal to alpha 1 x1, alpha 2 x2, alpha m xm, where alpha is f of ei. You follow that? Okay, therefore, now I know how it should look like. Notice that each fi is a first degree polynomial. Fi of x will be equal to alpha I1 x1 plus alpha Im xm. Okay, because for each I, it will be alpha 1 x1, alpha m xm, but this alpha 1, alpha m will depend on I, therefore I am writing for 1 does not equal to tm. Did you follow that? I runs from 1 to m, okay, 1 to n, whereas x1, x2, xm, these are scalars here. Now notice that this is a first degree polynomial in x1, x2, xm with the 0 constant term. Right? Therefore, what is that you have found out? Any linear map F from Rm to Rn is of this form. F of x1 to xm equal to alpha 1 1 x1 plus alpha 1 m xm dot alpha n1 x1 plus alpha n m xm. And these are all first degree polynomials with the 0 constant term. Pay attention, pause, review, proceed. In particular, if I say R2 to R4, if I give a map like this, f of xy equal to x squared, xy, x plus y, and phi x, is it a linear map? No, because this is not a first degree polynomial. No, okay. One of them is not first degree polynomial, it's not. Or if I give a map like this, f of xy equal to x plus 5, x, y, x plus y. So these are all first degree polynomial. This is also first degree polynomial. But is it a linear map? No, because this first degree polynomial has non-zero constant term. Therefore, this is not a linear map. This is also not a linear map. Okay. Go through these things. I have given some of the examples which are usually not done as soon as you introduce linear maps, because many teachers think they are a little abstract, but I think you will get used to it. You will also appreciate, because that will make your understanding of linear algebra much faster and better. Okay. So I hope all of you enjoyed. Please review. We will come back with a couple of more lectures on this before we try to prove other theorems which are already published. Okay, construction of linear maps, etc. They are already done, but you'll come to that. Okay, please go through it, and please mark your comments whether you like it or not. And if you appreciate some of the examples, leave your comments for that also. I will really appreciate that. Thank you very much.